Mr. Tarrou, in this algebra lesson, we are going to be talking about and setting up solving one-step equations. We're going to go through 3 examples where we read these word problems and we set up an equation that can represent or model these 3 situations. And then we're going to go through 6 more examples where we're solving these one-step equations, and we're going to put timestamps to those descriptions down in the description of this video if you want to skip ahead and go right to those examples and you don't need this introduction. So after we get these 3 word problems set up, we're going to be going through the 4 properties that are going to allow us to solve these one-step equations. The addition property of equality, subtraction property of equality, the multiplication property of equality, and finally the division property of equality. And then we're going to, over the next few lessons, move into 2-step equations, multi-step equations, eventually through algebraic studies, be doing solving equations which are equal proportions, and just, getting into more and more complex situations with these equations as we move through our algebra studies. And indeed, the skills that we're starting to learn in this lesson are going to carry through basically all other math classes that you study from here on out. So it's a very important skill. The very first part, though, is when you're given word problems, how do you set up the equation from that word problem? What type of equations or settings are we going to be looking at for solving these one-step equations? Well, how long will you need to drive to go 200 miles if you're traveling at a rate of 50 miles per hour? And okay, so there's 3 variables in here. How long, which is time. We're given a total distance which we're going to travel, and we're given a rate of speed, 50 miles per hour. And I could have written this out in full words and I'm just going to verbally say it though. When you're reading a word problem and you have 2 variables that are being compared together with the word per in between, that is an indication that you're being given a rate of change, which is a word problem verbiage for something called slope. When you learn how to graph linear equations, you're going to learn something about slope, and slope is rise over run, but with word problems that is a rate of change, and you'll again identify it often, not all the ways, with some kind of number and then a couple of variables after that. In the middle there's somewhere where you see the word per. And also the word per in word problems is an indication of division. So how long will you need to drive to go 200 miles? You're traveling 50 miles per hour. Okay, excluding like calculus and when things get really, really complicated, almost every problem you ever look at that deals motion and distance and time can be related by distance is equal to rate times time, or distance is equal to RT. So it says in this problem that we need to go a total distance of 200 miles. Now, then we've got a rate of change, a rate at which we're moving, and that's 50 miles per hour. So we're going to have 50 miles per hour, and that 50 miles per hour is going to be, that's our rate of movement, and now we have a period of time. Well, it is miles, that is 200 miles, per hour. So the rate or the amount of time, I can just write the word time, but specifically what we're going to be finding, because it's miles per hour, is the number of hours that it takes for you to travel that 200 miles. Now, if you've got a really good strong number sense, you might be able to look at this equation and just know that the answer is going to be 4. But there's going to be many algebra equations that you cannot just simply solve in your head with your sort of arithmetic skills. Not that they are very extremely important. Please don't grab a calculator every time you want to add or multiply or divide a couple of numbers, or especially work with fractions. So I'm not trying to, I don't want to downgrade the importance of knowing your basic arithmetics. They're the first most important thing that you know in mathematics. But as your teacher gives you these algebra equations, even if you can do them in your head, please practice the algebraic steps, the use of the properties we're going to cover to solve those equations, so that when you get into situations that you can't do the arithmetic in your head, you'll know how. If you earn $12 per hour, how many hours must you work to earn a total of $387? If you're just a If you're just working your way through maybe middle school or high school, you probably haven't actually worked yet. If you're a parent, maybe you're relearning this algebra to be able to help your kids. You understand about, hourly work. And there's all kind of situations of you guys watching these videos. So, what would be the equation that would model this situation? One way to figure out what that would be is simply go to, well, if I work 1 hour, I don't have enough room to make a table. I've done that in some other lessons as well. I'll have another link to lessons where you're setting up equations with more complicated situations, and it's often helpful to make a table of values to see that arithmetic pattern to help you develop the equation. So I could say, well, if I work 1 hour, then I've earned $12. If I've worked 2 hours, well, then that's a total of, 12 and 12 is $24. If I work 3 hours, because for every 1 hour that I work, I'm earning $12, that would be $10, $20, $30, $32, $34, $36. And maybe that, that arithmetic, working that arithmetic in your brain, or on a piece of scratch paper to develop this pattern, you'll realize, oh, every hour I work, I add another $12. Well, repeated addition is multiplication, right? So an equation to model the situation is your total pay of $387 is going to be calculated by taking the number of hours, the amount of money you're working or making, per hour, and multiplying that by the number of hours that you've worked. And so our equation is 387 equals 12 times the number of hours. Now, I can maybe say that I know that 5 times 4 is 20, so 50 times 4 is 200, but I'm not quite sure if I'm going to know right off the top of my head 12 times what is going to be equal to 387, so we need to use some kind of algebraic property to figure out or solve that equation. You currently have $130. How much will you need to save to purchase an item costing $215? Now, if I give my algebra students a question like this, often they'll just automatically know, oh, I need to save some more, so let's do 215 minus 130, which is absolutely correct. But to write it as an algebraic equation before seeing that subtraction that we need to find the answer, it's going to be that we have, oh, I've got $130. I want to add some unknown amount of money. Let's write savings to equal that total of 215. And all three of these examples in orange, I kind of already given away, can be solved with only one step. And that's what we're doing, solving one-step equations. And we kind of already, maybe your number sense will tell you that, to figure out the difference, it's going to be 215 minus 130. So the algebraic properties, though, that are making that happen, at least for these first two we're going to do or work with in our first three examples, these open sentences are equations. These open sentences mean the three that I just wrote here in orange. An open sentence is simply a sentence, an equation that has a variable in it, an open place to put or that is representing an unknown value. At this point in early algebra, it's just usually going to be a number, but it can represent other expressions as well. These open sentences are equations that can be solved in one step using the following properties. Addition property of equality. If for any real numbers of a, b, and c, if a is equal to b, then a plus c is equal to b plus c. Meaning that, I have two unknown quantities. They're being set equal to each other. But if I add the same value to both sides of the equation, I'm still going to get equivalent expressions. And the same thing is true with subtraction. You can subtract, if you have an equation that is set where two parts are set equal to each other and they're being defined as being equal, then I can subtract c from both sides and I'll still have equivalent statements. Now, this is more simple than what we're going to be looking at in the 6 examples to follow, but just to really nail this down home, if I say that 5 is equal to 5, okay? Now this is obviously true. I know that I wrote the same number on both sides. If I come in here and I'm just going to do addition just because, if I add 2 to both sides, I'm going to get a true statement. You know, I start with two items, two sides to an equation which are obviously equal. This is a closed sentence. There's no variables. I add 2 to both sides. I get another statement which is again true. That's what these properties are saying. Now, really, you can just about do anything you want to an equation as long as you do it once to each side. The equal sign is what breaks the left and right-hand side apart, or separates the left and right-hand side. If I come through here and you're like, oh, well, there's an addition property of equality and there's a subtraction property of equality. So, you know, like maybe I could just take this equation of 5 equals 5, this closed sentence, this closed equation, you know, I could, you know, why can't I add 2 to the left and subtract 2 to the right? Well, 5 plus 2 is, of course, still equal to 7, but 5 minus 2 is equal to 3, which, of course, is not equal. It's not correct. It's not true. So, yes, you have this addition property of equality. Yes, you have a subtraction property of equality, but see, you're adding the same value to both sides. You're subtracting the same value to both sides. You're doing whatever you want, really, to each side of the equation as long as you apply it once to each side. Now, let's just erase this incorrect or non-example. You're going to see me going through 6 examples. And before I start solving these 6 examples, oh, can't put this up if I got my eraser in the way. Let me get my fancy picture-in-picture out. Now there's more examples of inverse math operations, but to get the glare out of there, to solve for a variable in an open sentence, in an equation, you must isolate that variable. Simply get it alone. To move a number, variable, or term away from a variable that you're trying to solve for, yes, you can have an equation with more than one variable in it. This is only the beginning of us learning how to solve equations. So we're only going to have one variable in our equations. Okay, so to move a number, variable, or term, terms are separated by addition and subtraction in equations. We've already been talking about those when we started developing expressions. Away from a variable to the other side of the equation, to the other side of the equal sign, you must use an inverse math operation. You know, so we have a math operation of addition. What undoes addition? What's the inverse of addition? That's subtraction. I also use the word opposite all the time. That's probably not really mathematically great, but I always talk about what's the opposite of addition, which is subtraction. Really, I should be saying inverse. So if I slip up in the lesson, that's what I really mean. The inverse of subtraction is addition. The inverse of multiplication is division. Likewise, the inverse of division is multiplication, and this will develop into more and more mathematical operations as we move our way through algebra and algebra 2 and pre-calculus and into calculus. The inverse of square rooting, or the square root function, is to square both sides. You may or may not have worked with this math function, and you probably have not worked with this, but ultimately you'll be studying trigonometry, hopefully, as you move through your mathematics. And you know, if you're taking the sine of something, you can undo the sine function with its inverse function, which is arc sine or inverse sine. So there's many, many examples of inverse functions as you move your way through your math studies. And just to really try and drill this home, of maybe say how addition and subtraction are inverse math operations, you know, I could start with a value of, oh, let's say 7, add 2 to it, and of course I get 9. Now if I take 9 and I subtract 2, I get right back to 7, which is where I started. So you can see that the addition of 2 and the subtraction of 2, those math operations are undoing each other. And that's how you move a term or a number from one side of an equation over to the other. Now let's get on to those 6 examples. Alrighty then. For our first example, we've got x minus 3 is equal to 10. Now in the previous lesson where we introduced, you know, just what an equation, was, this would be an example where we would have done it with mental math. You know, what minus 3 is equal to 10? Well, I know it's 13, so the answer is 13. But, you know, what do you really need to do? What algebraic process do you need to go through solving this? Well, the addition, property of equality. You want to undo, and by the way, here's the equal sign coming down and dividing the left and right hand sides of this equation. I'm identifying the variable as being on the left hand side, and with that variable of x, the unknown, we have a subtraction of 3. So if I want to solve for x, I want to completely isolate it, get it alone. I don't want any addition or subtraction with it. I don't want a number out front or any kind of division. I just want x equals and then whatever. So the inverse math operation of subtraction is addition. So we're going to add 3 to both sides of the equation. Negative 3 plus 3 is equal to 0. Your teacher may want to see that, or you can just cross those out knowing that they're going to add up to be 0. And when you add by 0, that's the identity for addition. Adding by 0 doesn't really change anything, so you don't need to show that plus 0. And we've got the x coming down. Again, the negative 3 plus 3 is 0, so we have x is equal to 10 plus 3, which is equal to 13. Now, the absolute wonderful thing about equations, when you do these on your quiz or on your test for your teacher, you can check your own work. You know, if you believe that 13 is the solution, then what that means is when you plug a solution into an equation, the two sides become equal. It becomes a true statement. So if we think that 13 is the answer, we can say, hey, let's check this. So we have 13 minus 3. Does that indeed equal 10? And absolutely, yes, it does. So this is our final answer. X is equal to 13. Now moving on to a one-step equation that maybe we can't do in our head. We have negative 7 is equal to, so here comes our equal sign, separating the left side from the right-hand side of our equation. And that negative 7 is equal to 2/3 plus x. Now, I do not know, if I don't know off the top of my head that 2/3 plus some random number, well, it's not random, but I don't know what the number is to make that equal negative 7. So we are indeed going to need to actually work this out. And don't grab the calculator as soon as you see a fraction, please. And another thing, 2 divided by 3, like if you do struggle with fractions, and by the way, besides not being able to read a cooking book, not, in other many day-to-day examples, here's a ruler. It's a yardstick. It goes from 1 to 36 inches, and between each of these inches, there's a bunch of little marks in between those inch values, and those marks indicate what? Fractions. So if you want to build a frame, build a house, make anything, measure anything, you need to know how to work with fractions, just to get through day-to-day life, right? So stop making them into decimals, stop grabbing your calculator. If you do grab your calculator, 2 over 3, 2 divided by 3, yes, 2 divided by 3, that comes out to be 0.6 repeating. Well, some students will grab that on their calculator and write 0.67. They'll round that off, and that's nothing wrong with that. They might write 0.7. I don't know why I'm stuttering, but they might write 0.7. They might write 0.67. They might write 0.667. And that rounding off, with this fraction giving us a run-on decimal, that rounding off can, lead us to get a wrong answer when everything that we did besides that rounding was correct. So work with those fractions. And what we're going to do is we're going to see that on the right-hand side where the variable is, we have a positive 2/3 x. That's an addition of 2/3 with the x on that side. We could also rewrite that as negative 7 is equal to x, and there's nothing in front of that 2/3, so that's plus 2/3. My x is positive, and my 2/3 is positive, and these are equivalent. There's no real reason to really switch these two terms. On the right-hand side of this equation, terms are separated by addition and subtraction, so there's 2 here. All I'm doing is trying to illustrate to you that that is a positive 2/3 or a plus 2/3. So to undo that addition or that positive 2/3 on the right-hand side of this equation, we're going to do the inverse math operation, which is subtract. Now we have negative 7 minus 2/3. And then on the right we have positive 2/3 minus 2/3. Well, anything minus itself is going to come out to be 0. That's why we're introducing this inverse math operation. So on the right-hand side, we are just simply going to have x because that comes out to be 0. But maybe doing a little bit of scratch work on the side, how do you take negative 7 over 1 and subtract it with 2 over 3? Now notice instead of writing 7, I'm writing 7 over 1. Once you start working with fractions, I don't care if you multiply and dividing, adding and subtracting like we're doing here, you should make everything look like a fraction. So you can see the numerator and denominator with each of the items and probably terms that you are dealing with. You cannot add or subtract fractions unless you have common denominators. You want the lowest common multiple for the two denominators of those fractions. You want the lowest, that common denominator. So I know I just said the same thing twice, but I realize I might have misspoke a bit. So if I'm looking at our denominator of 1 and our denominator of 3, the multiples of 1, of course, are really just kind of counting by 1. And the multiples of 3, 3 times 1 is 3, 3 times 2 is equal to 6, 3 times 3 is 9, 3 times 4 is 12, and I'm just really counting by 3. And I want to identify, again, what is that lowest common multiple? Well, the multiple of 3 in that row starting with 1, the multiples of 1, that's the third number. I need to multiply 1 by 3 to get a common denominator. So we're going to introduce a multiple of 3 in the numerator and denominator of that first fraction. And that is going to give us negative 7 times 3 is negative 21 over 1 times 3 is equal to 3 minus 2 over 3. Now, why are we multiplying the numerator and denominator by the same value of 3? That fraction looks completely different, but 3 over 3, 3 divided by 3, anything divided by itself is equal to 1. So when I multiply by 1, like 5 times 1 is just 5, multiplying by 1 is the multiplicative identity. It doesn't change the value of what you're multiplying that 1 to. So I'm doing negative 7 over 1 and I'm multiplying it by 1, and I'm getting something that looks different, but I still just multiplied it by 1. So this has the same value. Negative 21 over 3 has the same value of negative 7 because, hey, negative 21 divided by 3 is negative 7. Now that we have those common denominators, we're going to combine those numbers on just the numerator. So negative 21 minus 2, that's going to come out to be negative 23 over 3. Minus 21, or negative 21 minus 2 is the same thing as negative 21 plus a negative 2, if you like to see it that way, to give you the negative 23. You can also, again, of course, negative movements are a movement to the left on the number line. So if you're at 0 and you move left 21 units for negative 21, and then 2 more units to the left 21 and left another 2 units, you're going to be at negative 23 on the number line. So however you need to think about it, that is the result of doing negative 7 minus 2/3. That does come out to be negative 23 over 3. Now, turning this improper fraction into a mixed fraction, if your teacher would like to see the answer that way, is you want to think to yourself, well, okay, this is division, right? How many 3's are in 23? Well, that would be 7, right? 7 times 3 is 21. Take away the 21, that leaves you with a remainder of 2, and 3 will not go into 2. You would have to introduce a decimal and a 0 and bring down the zeros and start going into decimals, but I want a mixed fraction. So that is my remainder, and this is a mixed fraction, is negative 7 and 2/3 is what is equal to x. Now, if I want to check my work, see if this is actually correct, again, all I got to do is take this, well, I don't want to work with the mixed fraction. Mixed fractions are wonderful for final answers. They're not good to work with, though. So if I want to check my answer, I'm going to go up here to negative 23 over 3. Notice I ignored that negative, by the way, as I went from improper form to mixed fraction form. Negative 7, this is my check. Negative 7 is equal to 2/3 minus 23 over 3. Well, that's going to be negative 7. I already have my common denominator of 3, so I can just copy that down and work with the top. 2 minus 23 is equal to 21. When you're combining numbers with different signs, you want to subtract those numbers and keep the sign of the largest absolute value, or basically 23 is bigger than 2, so that larger number is negative. So our final answer comes up to be negative 21. And negative 21 divided by 3 is equal to negative 7. And indeed, we get, when we plug negative 23 over 3 or negative 7 2/3 back into the original equation, we get two sides that match, and therefore this is our final answer. This has been a checked solution to that equation. Now over here we have our variable back on the left-hand side. Textbooks do tend to like to have that variable on the left more than the right, and so we get in the habit of always moving those numbers to the left, but we're not always moving our numbers to the left. We're moving those numbers away from the variable until we get it completely isolated. So on the left-hand side we have, again, a positive 2/5. You often will have the variable first. I'm putting these constants in front of the term or in front of the variable because, well, those are missed more often by my students. So I'm trying to go over some more of the difficult examples. So we want to undo this addition, this positive 2/5 that is with the x on the left. So the opposite of a positive 2/5 is to subtract 2/5. See, I just said the opposite again, the inverse math operation. The inverse of adding 2/5 to x is subtracting it. Anything minus itself is 0. Negative 2, or excuse me, 2 minus 2 is 0 over 5. Maybe let me go write that. 0 over 5. You cannot divide by 0, but you can divide into 0. Whenever 0 is in the numerator, that final fraction is going to be 0. But if this was 5 over 0, that would be undefined. But we can have 0 on the top. That answer is 0. So bringing down the x, we do not have common denominators. But I got plenty of room to write here, so I'm going to take, multiples of 4. 4, 8, 12, 16, 20, 24. Multiples of 5. 5, 10, 15, 20, 25. There's my lowest common multiple, my LCM. 4 needs to get multiplied by 1, 2, 3, 4, 5. And the 5 needs to get multiplied by 4. And that is going to give me 3 times 5 is 15. 4 times 5 is 20. Negative 2 times 4 is negative 8. And 5 times 4 is equal to 20. Now bringing these together, subtracting now just the numerators, now that we have the common denominator, 15 minus 8 is equal to 7. And our final answer is x is equal to 7 over 20. You want to check that? Always want to check your work. Many teachers require it. So our check, positive 2 over 5, x, which we believe is 7 over 20. Is that going to make the left side, when I plug in that 7 over 20, will it make the left side or equal to the right side, which is 3/4? I need a common denominator. Now, instead of doing the whole list here, this is 4 times 5 when you factor it. So this denominator has a factor of 5 and a factor of 4. This denominator only has a 5. So I need to introduce that factor of 4. So we're going to multiply 4 onto the numerator and denominator. Again, 4 over 4 is equal to 1, so I'm just multiplying by 1. I'm making the fraction look different, not changing its value. That's 8. That's 20. Bringing down the plus 7 over 20. Please note that I'm only doing one step at a time, by the way. Being very meticulous with my work, you should do that as well. It leads to much fewer mistakes. 8 times 7 is equal to 15. And now 15 is 3 times 5. 20 is 4 times 5. So the numerator and denominator both have a common factor of 5, and 5 divided by 5 is equal to 1. So we're left with a reduced value of 3/4, which is what the right-hand side was equal to. And that means that we have checked our solution. And there is how you solve one-step equations that deal with addition and subtraction, with a lot of review of fractions, because let's be honest, you know, I see a lot of students that unfortunately struggle with them, even though you really got it. There's a lot of day-to-day work that involves fractions, so please practice them. Please don't just grab your calculator as soon as you see one. It's going to weaken your math skills and make you struggle through classes that you'll take from here on out, and even finishing your Algebra 1 course. Now let's deal with one-step equations that involve multiplication and division. My last 4 examples are going to be dealing with the multiplication property of equality and the division property of equality. So I guess instead of doing 6 examples, I'm doing 7. If A is equal to B for any real number, A, B, and C, if A is equal to B, then A times C is equal to B times C. So you can multiply the same value to each side of the equation. You can also, if A is equal to B, then you can get an equivalent equation. The two sides are still going to be equal if you divide both sides by the same value, as long as C is not equal to 0, because you can't divide by 0. That's undefined, like I said just a moment ago. And really, it wouldn't make sense to multiply 0 to both sides of the equation either, because then you're just going to have 0 equals 0. Anything times 0 is 0, variables or numbers, because, well, all a variable is a number that we don't know. And why would you just completely get rid of a variable by multiplying it by 0? You'll have a true statement, but you won't know what what that unknown would have been to make the two sides equal. So really, that should just say C cannot equal 0 as well. So our first example of these 4 is going back to that original problem about the traveling question. You know, how many hours is it going to take for you to drive 200 miles if you're going 50 miles per hour? Now, again, we already knew it was equal to 4, or at least we can understand that if we know our mental math really well. But again, we have this equal sign separating the left side of the equation from the right. The variable is on the right-hand side of the equation this time. And with that variable of hours, we have a multiplication of 50. Whenever a number and a variable are touching, I know I wrote the entire word, but whenever a variable and a coefficient and a variable are touching, that means that they're connected by the math operation of a multiplication. And so the inverse math operation of multiplication is division. 50 divided by 50 is equal to 1, not 0, like sometimes students think, because if you were to then multiply by 0, your variable would be gone. But 50 divided by 50 is 1, so we're left with H, or hours. And when you're reducing this fraction here, both of these values ending with a 0 means that both 200 and 50, they're both divisible by 10. I can divide the top and bottom by 10, and 200 divided by 10 is 20, and 50 divided by 10 is equal to 5. And now that we're down to 20 over 5, those two numbers are also divisible by 5, and I can show that by dividing the numerator and denominator by 5, or I could write, and we're going to reduce that down to 4 over 1, or 4 hours. Or I could write that as 20 is equal to 4 times 5 over 5, and show that division of 5. Again, anything divided by itself is equal to 1, and that's another way of showing the reduction until you get down to 4 hours. So it is going to take you 4 hours to travel 200 miles if you are traveling at 50 miles per hour. Our second example over here is we have x divided by -2 is equal to 17. And a fraction bar, that's what it represents. A fraction bar represents division. So if you have a fraction, if you will, this is x divided by -2. You can look at it that way and go, well, hey, the opposite of dividing by -2 is to multiply both sides by -2. And you might write it like that. I think it'd be a very good idea to write that -2 over 1 to see the numerator and denominator of those fractions lining up. And there's all kinds of ways we can look at this. We can say, well, the -2 and the -2, I see this as division. I'm multiplication and division are inverse math operations. so they're going to cancel each other out, giving us x is equal to positive times negative is negative, 10 times 2 is 20, and 7 times 2 is 14, and 20 and 14 is going to be negative 34. Now, you could also say, well, negative 2 times the coefficient, the implied coefficient of 1 that's in front of the x, negative 2 times 1 is negative 2. Negative 1 times negative 2 is also negative 2. And then see that just reemphasizing just that much more, that it's negative 2 over negative 2, and anything divided by itself is equal to 1. And maybe just take one more step to write your final answer, that the unknown, the x, has to be equal to negative 34. And then to check your answer, is negative 34, which is what we believe x to be, divided by negative 2, is that indeed equal to 17? Well, when you divide two negatives, you get a positive answer, and 34 divided by 2 is indeed equal to 17. So we know that negative 34 is a correct answer. You know, one more way that you could write that original problem is you could have written it as recognizing the 1 that's in front of the x and just pull that fraction out front and write it as negative 1 over 2x is equal to 17. And then that example could be written to kind of look like our third example. We have 11 is equal to 2/5 x. Now, I can get rid of this coefficient of 2/5 in 2 steps. I can see the division of 5 and multiply both sides by 5. And we could, well, I wasn't going to show it, but we could multiply both sides by 5. That would give us 55 is equal to 2x, and then divide both sides by 2 and get whatever the final answer is going to be here in a second. But I would be working that out in 2 steps, which is okay if it helps you get the fractions done more accurately, but you don't have to do it in 2 steps. You can remember that with fractions, when you multiply reciprocals, that means when you flip a number like, negative 3/4 times negative 4/3, taking that fraction and writing the reciprocal, 3 times 4 is going to be negative 3 times negative 4 is going to be 12, and positive 4 over times positive 3 is going to be 12, and anything divided by itself is going to be equal to 1, or the 4 in the numerator, that factor of 4 in the numerator is going to cancel with this factor of 4 in that denominator, and likewise the 3's are going to cancel out, and you get 1 as well. When you multiply reciprocals, you always get an answer of 1. And that means you're just simply flipping the fraction, not changing the sign, just flipping the fraction. So if I want to get this coefficient to be 1 in 1 step, I multiply both sides of the equation. What color am I going to pick here? Well, it's already an orange, so let's pick green. I'm going to multiply both sides of this equation. Let's write it like this. I'm trying to keep the color separated so you can keep the examples clear. We're going to multiply both sides of this equation by 5 over 2. And again, seeing that now we have a multiplication of a fraction on the left-hand side of the equation, we're going to write that 11 to be over 1 so I can get the numerators and denominators to line up properly. And how many steps do I want to take this in? 2 times 5 is 10. 5 times 2 is 10x. We have 5 times 11, which is 55. And we have 2 times 1, which is going to be 2. And anything divided by itself is 1. So we're left down here with just x is equal to 55 over 2. And that's a perfect answer if your teacher is happy with a improper fraction. If you need to write your answer as a mixed fraction, well, 55 divided by 2, let's see here. 2 times 2 is 4. Subtract, bring that 1 down, bring down 15. How many 2's are in 15? That's going to be 7, right? And 2 times 7 is 14. That's going to give us a remainder of 1. And I don't know why I wrote it there because I'm running out of space. But that means our mixed fraction is going to be the equivalent of 55 over 2 is going to be 27 and 1/2. And if I want to make sure that this actually is indeed the correct answer, I would not work with the mixed fraction, but go to the improper one. And our check is going to be, I guess I could put it here, is 11 equal to 2 over 5 times 55 over 2. Well, these factors of 2 are going to cancel out, leaving us with 55 over 5, and that does come out to be 11. So the left and the right-hand sides do come out to be equal. I got one more example. Just to another example. Might as well call this a review of fractions. But another example dealing with fractions. We're going to start off with a mixed fraction. Make sure we get that written as an improper fraction, and then finish the example. Our last example, again with fractions, and I'm doing all these fractions not only because they're a weakness in a lot of they're a weak point in a lot of student skills, but there really isn't that much to solving one-step equations unless you have these more challenging problems. And so we have negative 3 and 4/5 x. Is it, what is the value of x that makes the left side of the equation equal to the right, which is 3/7? Okay, so again, mixed fractions are great. If I want to describe my height, I'm going to start off by saying that I'm 5 foot and then finish with the part of the remaining foot that I am equal to in height. They're nice for reporting a final value, but they're not nice to work with. So we're going to write this mixed fraction as an improper fraction. We're going to ignore the negative is there, and we're going to do 5 times 3, which is 15, and then we're going to add in that part, that remainder, if you will, that we that we would have gotten if we were dividing, of 4. So 3 times 5 is, or 5 times 3 is 15, plus 4 is 19 over 5 times x is equal to 3 over 7. But now don't forget that negative, and this is what we are solving for. Now again, to get rid of that coefficient, which is a fraction, we're going to multiply both sides of the equation by negative. I don't want to change the sign. Flip the fractions. We're going to have 5 over 19. And you can pretty much do whatever you want to an equation as long as you do it once to each side of the equation. And the 5 divided by 5 are going to cancel out, and the 19 divided by 19 are going to cancel out. Or you have to multiply these together and multiply these together, and you'll see that you have you got the same number, but you're dividing it by itself, so it is going to come out to be 1. And over here, we've got no common factors. So we have 3 times negative 5, which is negative 15 over... Okay, now, if I wanted to do 19 times 7 and, completely work it out by hand, we would, do 7 times 9 is 63, carry over the 6, and 7 times 1 is 7, and then 7 times 6 is going to be equal to, plus. 7 times 1 is 7, plus 6 is going to be 13, and thus we have 133. Now, you might have noticed when I do it verbally or mentally, I do 6 times the 1 in the tens place, so 6 times 10 is 70, and then, I think I just said 6. 7 times 1 is 70, if I did say it wrong, and 7 times 9 is 63. That's where that was stuck in my head. I don't know if I said it right or wrong, but 70 and 63, if you can add those in your head, with the 7 and the 6 being 13, you can get 133 with mental math. And that is the final answer. If you want to make sure that this is actually going to be the correct answer, or is the correct answer, I suggest not plugging it into the original problem, but plugging it into here where you have the improper fraction, and check, does negative 19 over 5 times negative 15 over 133, does that indeed equal 3 over 7? And it will check out, and that is the end of my last example. I'm Mr. Tarrou. Bam! Go do your homework.